Okay, so hi everybody. So it's lecture 26. And this is, I guess, the second last lecture, and we're going to do some more graph theory. And then in the next lecture, we'll maybe do a tiny bit more and then just do a review. So in this lecture, I want to do three things. So one is I want to introduce a definition, which I already hinted at in the homework, which is the definition of a connected component. And then I want to prove a very interesting theorem going back to our original bridges of Königsberg problem, which is called Euler's theorem. Which is, maybe it's one of the most complicated proofs we'll see in the course, but we'll use a lot of the graph theoretic concepts we've developed so far for that. And then finally, if I have time, I'll talk about K coloring. So we've talked about two coloring, and then we'll discuss K coloring. So let me start by saying what a connected component is. Here's the definition. So a connected component of a graph G is a maximal connected subgraph of G. So is a maximal connected subgraph H contained in G. And the most important word here, well, okay, the word connected is important, but a very important word here, which may be new, is the word maximal. And maximal means that if you add any edges to H, it wouldn't be a connected subgraph anymore. Okay, so so this would make it either disconnected or not a subgraph of G. So so among subgraphs, adding any edges would make the graph disconnected, let's say, or not a subgraph. Okay, so this is actually a very simple concept. Let me just show you an example. Sorry, my charger is looking kind of funny.
What do you mean when you say that adding edges could make it disconnected?
Yeah, so let me clarify that, but I'm just confused about what's happening with my charger now. Okay. So for example, here's a graph. So now there are various subgraphs here. So I could consider just this edge. Sorry. I could consider just this edge here. So that's a connected subgraph, but it's not maximal because I can add another edge to it. And it's still a connected subgraph. That's also not maximal. I can add one more edge to it. That's a connected subgraph. But now I can't add any edges. If I add any more edges to the subgraph, such as, say, this one, I'm going to end up with a disconnected graph. And so this is a connected component. Let's call this. So this is one connected component. Let's call it H1. And the rest of the graph, I can do the same thing. So this is a connected component because I can't add any edges to it to make it well, okay. How about, let to be very clear, let's adding edges or vertices. Okay, so I could consider adding that isolated vertex to this, but then that would make it disconnected. So this is another connected component. And this is also a connected component. This is trivially connected. And you can't add anything else in the graph to it that preserves being connected and being a subgraph. So what do we see from, so any questions about this example?
I have a question.
Yep.
Does a graph G only have one connected component? But like if, for example, you had a graph G that was two disconnected trees of length with three vertices each, would they both be maximal? Would they both be connected components of G? Or?
Yeah. Okay. Good. So it's a great question. So you're asking, let's say you have a graph like this, right? So, and you're asking, well, would these both be connected components? The answer is yes. So maximal does not mean maximum. So you can have many, maximal means for each subgraph, you cannot add anything more, say any more edges or vertices to that particular one while preserving the property of being a connected subgraph. So this is a connected subgraph, and this is a maximal connected subgraph, and so is this. So we don't care about the size.
Okay, thank you.
Okay, so it's a great question. And so there's a general remark, which we won't prove, but it's easy to prove. So every graph is a union of its connected components. Okay, so for every graph, you can break it into connected components. You find a connected component, you remove it, you keep doing this. So that's the first thing I want to say. And I mean, okay, it's a disjoint union. The connected components are disjoint also. Two connected components cannot share a vertex. Why is that?
Because if they shared a vertex, we could create a larger component.
Yeah, exactly. So it's a disjoint union. And the other property is that there are no edges between the connected components. So let me just be precise. If G has connected components, so let's write this as G equals H1 union H2 union all the way up to HK. So it's a vertex disjoint. So the vertices of the connected components are disjoint. And now the second thing I want to say is that there are no edges between the connected components. Between two distinct connected components. Why is that?
For the same reason as like why you can't share a vertex.
It's the same kind of reason, right? If you had, let's say, an edge between these two, then you could merge them, right? You could add an edge and get a bigger connected component. So this is by maximality. Both of these things are by maximality. So this maximal gives you this very nice structure that these components are disjoint and there are no edges between them. And by the way, if a graph is connected, how many connected components does it have? Anyone?
It should
One.
only have.
Yeah, it should just have one. Exactly. So a G is connected if and only if it has one connected component. this is not so hard to see. Okay, if it has one connected component, then well, it's connected. But if it has two connected components, well, then there's no path between vertices in one and vertices in the other one, so it's disconnected. So it's an if and only if. So this is not it's not a complicated concept. But any questions about these remarks or the definition? Okay, so now we're going to use this as one of the concepts. And by the way, this is also useful in the homework to prove Euler's theorem, which is the first theorem in graph theory, which comes back to the first thing we studied in this course. So let's recall a few things. So let's recall what an Euler circuit is. So an Eulerian circuit of a graph G is a simple circuit, or is a circuit which uses every edge exactly once. So we discussed this earlier. And we proved a theorem about it also, right? We showed that if a graph is connected and it has, if a graph has an Eulerian circuit, let's say, I'm using CKT for circuit, then all the degrees have to be even. That was the first thing we showed in the first lecture on graph theory. So all degrees are even and G is connected. I mean, the connected part is kind of easy, right? If there's a Eulerian circuit, then just by following the circuit, you can go from anywhere to anywhere. Or actually, sorry, I guess there's this annoying thing about you could add an isolated vertex. So let's just assume yeah, let's assume the graph is connected. Well, you don't actually even need connected. Okay, this is what we showed. If a graph has an Eulerian circuit, then all the degrees have to be even. Now, Euler's theorem is the converse to this, which is a much more interesting direction. So you could ask, is the converse true? That if you show me a graph and all the degrees are even, then does it have to have an Eulerian circuit? This is a lot more surprising because checking degrees of a graph is easy, right? You just count the number of edges for every vertex. Finding an Eulerian circuit might be kind of tricky. It's this very global thing. And this is exactly Euler's theorem. So the theorem says, if G is a connected multigraph with at least two vertices, and the degrees of all vertices are even, then it has an Eulerian circuit. Okay, so before we prove this, I just want to show you how powerful this theorem is. So the assumption is, okay, connected, at least two vertices, and degree V is even. This is the key assumption. And conclusion is that there's an Eulerian circuit. So let's look at some examples. So let me just draw an example here. So let's consider this graph. Okay. Actually, let's draw two graphs. And let me just add one more edge in this graph. Now, if I showed you these graphs and I said, hey, do these have an Eulerian circuit? It's not obvious how to find one. You'd have to try some stuff, right? What the theorem is saying is all you have to do is look at the degrees. So the degrees are 2, 2, 4, 4, 2, 2, 2, 3, and 3. So the first graph, it has some odd degrees, right? And so even by our original theorem up here, if there was an Eulerian circuit, the degrees would be even, right? Sorry, by this theorem here. So this graph cannot have an Eulerian circuit because it has these odd degree vertices. Now, the beauty of this theorem that we're about to show is if you look at the second graph, then let's look at the degrees. There are 2, 2, 4, 4, 2, 2, 2, 4, 4. These are all even. There's a connected multigraph with at least two vertices, all degrees are even. The theorem says this has to have an Eulerian circuit, right? Just without even doing anything, we just know that it has to by checking this very local condition. So the beauty of this theorem is that this is easy to check because it's very local. You don't have to look at the whole graph to decide whether the degrees are even. You just look at the vertices one by one, and this is hard, potentially hard, because it's global. So this is a type of theorem that's very important in math and in graph theory generally, that sometimes there's some difficult global property of an object, maybe a graph or some equations or something that's implied by some easy thing. And that's a very common theme in math. So any questions about the statement before we proceed to the proof?
I just have a small question about the graph.
Mhm.
Wouldn't it be degree 5 and 6, or is it not connected there? One of the two threes, one should be degree 5, right?
Oh,
Or
sorry,
is-
yeah, sorry.
Oh.
That one should be degree 5. Sorry, my bad.
Oh, thank you. And then
So this
the other
should
one
be
should be
5.
6.
This should be 6. Yeah, I miscounted. Okay, so even this, I guess, easy problem, you can make a mistake. But yeah, you are right. Any other comments? Okay, so let's move. So this was proven in, I guess, 1736. Euler. So let's prove this. So before we prove this, we're going to prove a lemma. So a lemma is just a proposition that's useful in proving a theorem. This lemma might also be useful for the homework. Here's the lemma. So if G is a multigraph, and every vertex has degree at least 2, then G has to contain a cycle. A cycle is a simple circuit. So that's a circuit where no edges are repeated. Okay. So this is another kind of, this is like a baby version of this theorem. It's saying, well, if all the degrees are at least 2, I might not be able to find an Euler circuit, but I can find a circuit. So there are multiple ways to prove this, and I'm going to give you a proof that uses trees, just because I want to show you that this is connected to trees in some way. Any questions about the statement before we prove this?
When you say a multigraph, does that include the graphs that don't have multiple paths connecting
Yeah,
to
so
vertices?
this says may have multiple edges. Doesn't have to, but may have multiple edges, such as the pictures above. But no loops. We're not doing loops in this course. So loops are like a vertex connected to itself. We're not doing that. Okay. So let's prove this as a very slick proof that uses the idea of connected components and trees. So what's the proof? Well, we'll show the contrapositive. So what's the contrapositive? Well, the theorem is saying if the degrees are bigger than 2, then there's a simple circuit. So the contrapositive is if there's no simple circuit, then there must be a vertex with degree strictly less than 2, right? So assume G is acyclic. So that means it doesn't have any simple circuit. Now, it may or may not be connected. But whatever it is, we can look at its connected components. So let G1 through GK be the connected components of G. Every graph can be broken into a disjoint union of connected components. Now, if G doesn't have any cycles, then the connected components also don't have cycles. You can't create a cycle by going to a subgraph. So G1 through GK are acyclic since they're subgraphs and connected. So what's that called?
Tree.
Yeah. So they are trees. So the picture that's going on in the proof is something like, well, you have this big graph. It might not be a tree, but it's a disjoint union of trees. And these are the connected components. So any acyclic graph is a disjoint union of trees. Okay, so now, oh, by the way, there could be some isolated vertices as well, right? That's allowed. And now, where's the degree? Where's the vertex with degree less than 2?
Choose any of the trees and then like the leaf of or a leaf of that tree.
Yeah, so last time we
yes.
proved that every tree has a leaf, which is a vertex of degree 1. So you have to be a little careful because there could be isolated vertices. So really now you say, okay, if some GI has at least 2 vertices, it must have a leaf. And then that leaf has degree 1 in G, right? It must have a leaf L, and the degree of L equals 1 in G. So I'm done. Otherwise, they all have 1 vertex. So otherwise, each GI is isolated or is a single vertex of degree 0. in G. That's it. Right? So if it's acyclic, it's a bunch of trees, and trees have leaves. The only slightly tricky thing that can happen is isolated vertices, but those also have degree less than 2. So notice that here, it's a matter of style. I've written in G. And why have I written in G?
You remind us that this has to do with our original graph and hence applies really strongly to our lemma.
Yeah, so this is a good general practice that if you're writing a proof with multiple graphs and you're using terminology like connected or degrees or whatever, be sure to say which graph it's in, because that could mean different things. So that's the proof of the lemma. So now let's move on to the proof of the theorem. So the theorem is if it's connected with at least 2 vertices and the degrees are even, then there's an Euler circuit. Okay, so the proof is going to be by induction. By induction on what? So in graph theory, there's typically 2 kinds of, I mean, there are many, but the 2 basic kinds are induction on the number of edges and induction on the number of vertices. And in this case, we're going to do number of edges. Okay, so I'm going to consider I'm going to let P of M be the statement I want to prove that if you have a connected multigraph with at least 2 vertices and the degrees are even, then there's an Eulerian circuit for graphs with up to M edge for graphs with M edges. So this is just saying if G has M edges and it's connected and the degrees are even and it has at least 2 vertices, then G has an Euler circuit. So just saying the theorem is true for graphs with M edges. Now, what's the base case? So this requires a little bit of thought. So anybody have any thought about what the smallest graph is to which, for which the statement applies?
A multigraph with 2 vertices.
Yeah, so
Like
the base case is M equals 2. Because if you have less than 2 edges, then you have either 1 edge or 0 edges. If you have 0 edges, well, the only way you're connected is you have 1 vertex, so it doesn't count. If you have 1 edge, then the degrees aren't even. So the base case is M equals 2. The only graph satisfying the hypotheses is this graph, for which the conclusion is true. Well, which has an Euler circuit, right? It has a clear Euler circuit. You just do this. So that required a little bit of thought. I mean, as with many inductive proofs, the key is to set this up right. So here we're using all of the conditions that there are at least 2 vertices, the degrees are even, it's connected, etc. So that's the base case. Any questions or comments on the base case? Okay, let's do the inductive step. Now here it'll be convenient to do strong induction. So let's assume all of these statements, P2 up through PM. And now we want to show PM plus 1. So let's G equal VE. Be a connected multigraph with even degrees, at least 2 vertices, and exactly m plus 1 edges. Um, okay. I mean, yeah, okay. The reason I'm sort of pausing here is I'm getting a little concerned about, can you even have, could there be some even odd kind of issue here that, can you have a graph with an odd number of edges where all the degrees are even? We'll think about this later. Let's see if this comes up anywhere in the proof. I don't think it will. Okay. So so we have this graph G. Let's draw a picture of it. Let's just have a running example just to see how the proof goes. Let's look at a simplified version of the graph we saw earlier. So that's our graph G. Now to do induction, I need to produce a graph with less edges, right? I want to use the inductive hypothesis. So now what I'm going to do, so any ideas about how to get a smaller graph out of this, which still has the same properties?
We break it up into simple circuits.
Break it up into simple circuits. Okay, that's a good thought. We don't yet know how to do that, but we do know how to find a simple circuit, right? The lemma tells us that if the degrees are at least 2, then it has a simple circuit. So now this graph, so G, all the degrees are at least 2 because they're all even and they can't be 0 because it's connected, right? So notice the degree of V is at least 2 for all V in V since G is connected. You can't have 0 degree vertices, right? So then by the lemma, there exists a cycle. C. Now we don't really have any, we don't really have any control over what the C is. It could be anything. So let's say the dilemma spits out this circuit C that does this. So I guess that has a direction. So let's say the lemma gives us this C. That's not an, so okay, if that was an Euler circuit, great, we're done, right? If the lemma gave us an Euler circuit, excellent. right? So if C equals G, or if C is an Euler circuit, we're done. Otherwise, there's some other stuff left over. And this is where the induction is going to come in. So otherwise, what I'm going to do is I'm going to remove C. So otherwise, let H be the graph that I get from taking G and removing the edges of C. So EC, okay, so let's say C is, it's on some set of vertices, VC, and it has some set of edges, EC. So let's, I mean, okay, I'm viewing the simple circuit as a graph, but that's okay. Every edge appears once, so it's a multigraph. So this is the graph obtained by deleting the edges of C. So in this picture over here, when I delete C, I hope it allows me to erase just pieces of this picture. What's going to happen is I'm going to erase all the edges of C. Okay, but sorry, but not the vertices. So the vertices are still there. So these vertices are here. These vertices are here, but now I've deleted all the edges of C. So this is my graph H. Okay, so these isolated vertices are not very interesting. What I'm going to do now is I'm going to look at all the connected components of H, which have at least two vertices. Because remember, my theorem that I want to prove, my inductive hypothesis, it only applies to graphs with at least two vertices. So now I'm going to let H1 to HK be the connected components of H with at least two vertices. So in this running example, the connected components are this and this. So there's H1 and H2. Any questions about the definition of H1, H2, HK before we proceed?
I had a question about the circuit C that you removed.
Yeah.
Doesn't a simple circuit not repeat vertices other than the first and last one? But like the center vertex in C, don't you cross?
No, it's allowed to repeat vertices. It means no repeated edges. It's a great question. It's a very common confusion even for me. But the way we've defined simple circuit is it doesn't repeat edges. Does that answer your question?
Yeah, thank you.
Okay. So now we're kind of, now I claim we can do induction on what's left. Now to do induction on what's left, it has to satisfy all the, all the properties that are needed for the inductive hypothesis to kick in, which are that it better be a connected graph, multigraph, with less than m edges, at least two vertices, and all degrees even. So let's check all of those, right? So observe. So each of these things is connected. Why is it connected?
Because we've defined it to be a connected component.
Yeah, because it's a connected component. here's a more interesting. So each HI has each is connected and has at least 2 vertices. We defined it that way. It's a multigraph. And now I claim that it has even degrees. Even degree in the HI. Now, why is that?
We knew beforehand, before we removed the simple circuit, that everything had even degree, like every vertice, and by remove, so anything that was not connected or not a vertice that was used in the simple circuit is already fine, and anything that was used in the simple circuit will have an even number of edges removed because something must have entered and then left, and used an even number of edges.
So we're kind of using, a special case of the other side of the theorem that we proved, which is when you have a simple circuit, then all the degrees are even. So this is because since removing C removes an even number of edges incident to every vertex in G. And the degree of every vertex in G was even. So yeah, and right? So we started with even degree, we removed an even number of edges because of the simple cycle. And so we still have an even number of edges. So this is a key observation. And that's, I think, all we need for the induction hypothesis, right? Degrees are, the graph is connected, degrees are even, at least 2 vertices, and it has a number of edges which is less than M, because I removed at least 2 edges when I removed C. Okay, so H has, so each has at most M plus 1 minus the number of edges in C, which is less than M minus 1 edges. So each of these graphs has fewer edges. So by the inductive hypothesis, each of them has an Euler circuit. Now, okay, before invoking the induction hypothesis, I'm actually going to make one more claim, which is going to be useful in completing the induction. But any questions about these observations? Okay, so the trickiest part of this proof, in some ways, I mean, the trickiest part is just coming up with the scheme, but a subtlety in this proof now is we have to now show that the original circuit C touches each of these HIs. So we have to show that each of these HIs has a vertex that actually belongs to C. So I'm going to write this claim. We'll prove the claim later. So the claim is for every I going from 1 to K, there exists a vertex Si in Hi such that Si is also in this cycle C. it may not be unique. So in the picture here, what we're saying is that there's at least one vertex, in this case, this vertex and this vertex, which also belong to the cycle. That in each of these connected components that you had left, they actually touch the cycle in at least one place. That's what the claim is saying. It's kind of intuitively true. We'll prove it in a moment. But we're going to use it. I'll show you why it's useful before proving it. Otherwise, it's not very well motivated. So is the statement of the claim clear? So in this case, this would be the vertex S1, and this would be the vertex S2. That belongs to both H1, H2, and to the cycle. Now, given the claim, it's easy to complete the induction. Now, what's the idea? Well, the idea is, this, maybe I should use a new color for this. By the inductive hypothesis, there's an Euler circuit inside H1 and H2, right? So by the inductive hypothesis, I can find some little Euler circuits inside H1 and H2, and I can make them start and end at S1 and S2. I can just always do that, right? If I have an Euler circuit in our graph, I can pretend it starts and ends at any of the vertices. And now, any thoughts on how I can combine all of this to get an Euler circuit of the whole graph?
At the point where C touches a vertex that's shared with one of either H1 or H2, you can just follow the circuit of H2 or H1 back to the vertex that you left off on and continue along C.
Exactly. So the idea is going to be that, I have these two pictures. So this was my original C, and now I also had this H1 and H2. And the idea is that I'm going to, I don't know how good my drawing skills are going to be. The idea is that I can glue all of this stuff together to get, the idea is that I'm going to, so before I write the proof, let me mention say this is the idea, is that so this I use the inductive hypothesis. Here I use the lemma. And now I can glue all of this stuff together to get one big Eulerian circuit. But I need these gluing points to be able to do that. And this is actually not so hard to write in a proof. So now observe. So now, okay. So by the inductive hypothesis, each of these connected components, Hi, has its own little Euler tour, right? So each Hi has an Euler circuit. Let's call it Ci. Starting and ending at this special green vertex Si, which is in Hi and in C. Okay, so Ci's are these like blue little tours here. This is C1, this is C2. Yeah, this is H1, this is H2. And now I just glue them together. So now let C prime be C, but replacing the first occurrence of Si with Ci for I going from 1 to k. Okay, so for each time one of these portal vertices appears in C, I'm going to replace it by this blue circuit Ci. This is the punchline. And now this is an Euler circuit of the whole graph, because it uses every edge in H, and it also uses every edge in C. So it uses every edge in G. Well, since it's a circuit, first of all. So here I'm using this property of circuits, that if I take a circuit and I replace a vertex in it by another circuit, by a simple circuit with different edges, then I get another circuit, since it is a circuit which uses every edge. Of G, which is H union H1 union up to H. Okay, exactly once. So that's it. That completes the proof, except for the claim. So I have to prove still the claim. So this completes the proof, except for the claim. And now this is again, I'm doing this kind of intentionally because sometimes this is how you write a proof in a mathematical paper, that you don't always write it in order. You say, hey, I'm going to prove this claim later, but given the claim, here's how you finish the proof, because it's easier to follow the argument that way. But now I have to prove this claim. But before I prove the claim, any questions? So a lot of stuff happened in this proof, right? First, we proved this lemma. Then we came up with this very particular induction hypothesis. Then we extracted the cycle. We looked at the subgraph. The key was that they had fewer edges, but they still had even degree. So we could find little Euler circuits there, and then we could glue them all together. But now we have to prove the claim. So let's prove the claim. We make a copy of it. Okay, well, this is not too hard. So before we prove it, any thoughts on why it's true? Why does the cycle have to touch these HIs?
If it didn't, G wouldn't be connected.
If it didn't, G wouldn't be connected. Yeah, that's the right intuition. So it requires a little bit of care to prove it. Let me just do the proof in full detail. So I'll just copy this picture over so we can keep track of it. Well, okay, so let's say I have some HI. So consider HI. So fix some I and look at that HI. Now the main claim is that there has to be an edge incident with one endpoint in HI and one endpoint outside HI. Okay, so observe that there is some edge, let's call it SI, in G, in the big graph, such that SI is in HI, but the other endpoint is not in HI. Now, why is that? Well, just if you have this HI here, and then you have the rest, it's sitting in this big graph G. If there were no edges going out of here, then as Ben said, G would be disconnected, right? Otherwise, there would be no path between, of any vertex in HI and any vertex outside HI, right? So otherwise, there would be no path between any vertex in HI and any vertex in the vertex set of G minus HI. So in, let's say, V minus V vertex set of HI. So we have our hands on this one edge, SITI, that's going out of HI.
And
Any
then
questions on this step? Okay. So now what we're going to observe, so make sure I get this right. Good, yeah. Now we're going to do something kind of subtle. So how did we get HI? Well, HI was a connected component of H, right? A connected component is a maximal connected subgraph. So now I'm going to say that actually this edge SITI cannot be an H. Moreover, the edge SITI is not an edge of H. Why? Well, if it was, I could add it to this subgraph to get a bigger connected component. So remember, connected component is a maximal connected subgraph, right? Adding edges would make it disconnected or not a subgraph. And in this case, yeah, if this edge was inside H, so a larger connected component in H. So important to annotate because there's so many graphs floating around now. There's G, there's H, and there's HI. Right? The key fact we're using here is that HI is a connected component in H. So actually this edge, so now we have two things. This edge belongs to G, and the edge does not belong to H. And remember, H is G minus C. So the only way this is possible is that this edge belongs to the cycle. And if the edge belongs to the cycle, the vertex belongs to the cycle. Okay, so it's a weirdly tricky argument, this claim. So we go through it again. What do we use? Well, we use that G is connected. So there has to be some edge coming out of HI, but that edge cannot be an H because HI is a maximal connected subgraph of H. So that edge has to be in C. And then we're in business, right? There's an edge of the cycle touching HI. So that's it. That completes the proof of Euler's theorem. The proof by induction. And, we really use, I think this is an interesting proof. It's by far the most complicated proof we've done in the course, I would say. It's interesting to see that all the hypotheses are used, right? That we you know, so for example, where did we use that the graph is connected?
When justifying our claim.
When justifying who?
Our claim, to show that we had
Yeah.
an edge that connected HI to the outside world.
Yeah, so we used here that G is connected. This is impossible because G is connected. Where did we use that? Where do we use that G has at least two vertices? Why was it important that the base case involved a graph with two vertices?
So that our lemma applied?
Well, so the lemma just requires all the degrees to be at least two. Okay, so, well,
Oh, yeah.
not quite. We just use G is connected and degree at least two. But why is it important when we peel off like what would go? I mean, okay, I guess you need the two vertices just because without the two vertices there's no base case. It's just simply not true. If you have less than two vertices, the graph may not have an Euler circuit. But importantly, what we did, one thing we used here implicitly is that the cycle always has at least two edges. And that's why the total number of edges went down. Okay, here's one question. Could we have done induction on the vertices? So what happens if you try to do the same proof, but you do induction on vertices? So you start with a graph. Okay, it has at least two vertices. It has even degrees. You use the lemma. You get this C. Can we do induction on vertices?
I mean, not necessarily, because our graph could still be connected after we delete C, I believe.
Yeah, so the answer is no, because what you're removing is an edge subgraph, right? You're removing the edges of the cycle. So this wouldn't work if the following thing happened. Let's say you have a graph like this. And let's say your cycle that you removed was just, okay, it's a horrible picture. Sorry. Your cycle that you remove is just this part up here. Right? Well, yeah, you could remove that, but then the number of vertices doesn't go down. Okay, so it was actually important to do induction on the edges here. So in general, when you're reading a complicated proof like this, to really understand it, you should ask yourself, were all the hypotheses used? And what, could I have simplified it? Could I have varied the proof in some way? And that way you really find the limitations of the proof, and you also find you end up understanding the structure of the problem better. So any questions or comments on this proof? I know this was a lot, but in the end, you have this very clean statement.
Could we have somehow induced on vertices by applying the lemma multiple times?
That's a good question. So could we have induced on vertices applying the lemma multiple times? Well, let's think about it. Well, okay, what about this example? So just two vertices where you have a ton of edges. I mean, you know, of course it's fine, but you'd have to, I mean, you'd have to make some argument saying you're trying to say that if you apply the lemma enough times, then the number of vertices has to go down, right? That doesn't really happen in this example.
Well, I think eventually what I would say is you have to reach a vertex of degree 0, at which point you have multiple connected components.
I see.
It's still nasty.
Yeah. Okay. I see what you're saying. You're saying that if you keep applying the lemma, the number of edges is going down. So you will eventually reach a vertex of degree 0. Yeah, okay, you could do that. It would work, actually. So you need to make the additional argument you're making is that you're kind of doing an induction within an induction. You're saying that, well, the graph is finite. So if you keep applying the lemma. Now, the thing I think I'm bothered by is how would you glue all those things together? So, so you know, you could probably make it work, but the gluing might be a little bit harder. So this proof is, you know, one of the beautiful things about it is that, you know, is that there's this easy way to glue the little circuits into a big one. And these green vertices are really what's allowing you to pull this off. Otherwise, if you just keep pulling off cycles in some disorganized way, you need some additional argument to say you can glue them all to get an Euler tour. It's not obvious. Any other comments? Okay, well, that took a while, so I'm not going to get to prove the main theorem on K coloring. But let me just state the definition of coloring and do some examples. Any last questions on this? Okay. Okay, so we've already talked about two coloring. K coloring is just a straightforward generalization of this. So let me write the definition. A K coloring of a graph is a function f from the vertices to what variable did we use for two coloring? Did we use f? We did, right? Yeah, I think so. To the set of numbers 1 through k, such that for every pair of vertices, if that pair is an edge, then the colors are different. So it's like two coloring, except you have more than, you have more colors. Let's look at some example. And okay, the minimum K, sorry, that's unreadable. Such that G is K colorable is called its chromatic number. So let's look at some examples. What's the chromatic number of the triangle?
3.
3. So you need 3 colors because, well, if you had less than 3, because all pairs are connected, right? So if you had 2 colors, then 2 of them would be the same color and they'd be connected. So you need 3 colors. So it's 3 colorable and it's not 2 colorable. So in general, the complete graph. So the complete graph means you just take a bunch of vertices and look at all possible edges between them. How many colors do you need for the complete graph on n vertices?
N.
N. Why?
Because if you had less than n by the pigeonhole principle, you'd have 2 vertices with the same color, and those 2 vertices have an edge. So that wouldn't work.
Yeah. So any K coloring with K less than n, or okay, it wouldn't be a K coloring. So let's just say there's no K coloring with K less than n by pigeonhole. What that means is that if you had less than n colors, then there would be 2 vertices that got the same color. But then they'd be connected by an edge because all pairs are connected by edges. So that wouldn't be a coloring. So then the chromatic number, okay, this is denoted chi of G. The chromatic number of the complete graph on n vertices. So we just said it can't be less than n. Could it be equal to n?
Yeah, if we just color each vertex a different color.
Yeah, if you color each vertex a different color, then no 2 vertices have the same color regardless of whether or not they're connected. So it's n. Here's another interesting example. What about a tree? Any tree.
Shouldn't a tree be 2 colorable always?
Why?
Because we're never gonna have like cycles looping back, and so
Yeah.
we can always.
This has no odd cycle. Well, because it has no cycle at all. So it doesn't have odd cycle. So this is actually 2 colorable. So the chromatic number of any tree is just 2. Now, it's not so easy to find a coloring. So if you've studied computer science, it's actually, it's NP hard. It's hard. It's not easy in general to find colorings. Coloring, I'll give you an example showing you, well, maybe I'll give the example next time. Yeah, what do I want to say about coloring? Yeah, I want to make one remark about coloring. So the remark is, if a graph is k-colorable, then if you look at the following sets, then the subgraphs, or then the subsets, V1, this is the set of vertices which get the color 1, all the way up to Vk, which is a set of vertices that get the color k. Well, inside each subset, there are no edges. Okay, so the picture is, if a graph is k-colorable, there's a way to partition it into these subsets, V1, V2, all the way up to Vk. And the subsets are just defined to be those vertices that are given a particular color. Now, what was the definition of colorability? Well, the definition was whenever there's an edge, the colors are different. The contrapositive is if the colors are the same, there's no edge. So it means that there are no edges inside here, and all the edges go between these subsets. So this is another interpretation of colorability, that you can partition the vertices into k sets so that all the edges are between distinct sets. And this property is called k-partiteness. So k-colorability and k-partiteness are the same thing. I don't want to burden you with jargon, but if you see this terminology later in life, then it's just the same thing as k-colorable. Colorable, and the k equals 2 cases called bipartite. Okay, so the theorem that we're going to prove next time is another local to global theorem. Well, yeah, saying that if all the degrees in a graph are at most some number d, so then the chromatic number of the graph is bounded by the maximum degree plus 1. So bound on the degrees gives you a bound on the chromatic number. So it's again a local to global kind of theorem because this is easy to check. And this is maybe hard. And that's the last theorem we're going to prove in graph theory. So let me end with a little mind map of all the stuff we've proven in graph theory. We've essentially covered 4 or 5 concepts. So one is the concept of degrees. Another is the concept of a graph being connected. Then we've covered we've talked about cycles. And we've proved, okay, we've talked about trees. And we've proved a bunch of theorems connecting these different concepts. And okay, maybe k-colorable. So, the first theorem we proved is that, if the degrees are even, then you get Euler circuit. Oh, sorry, we just proved that. And in fact, it kind of goes both ways. Even degrees if and only if there's an Euler circuit. So that's a connection between degrees and cycles in the graph. The theorem we're going to prove next time is that if the degree is bounded, then the graph is k-colorable. So this is that the chromatic number is at most the maximum degree plus 1. And then, we proved that a graph is two colorable if and only if it has no odd cycles in the first lecture. And then, okay, I guess connectedness came into this Euler theorem as well. Now, trees are these graphs that are, don't have cycles and are connected, and were kind of used to prove some of these other theorems. And a graph is connected if and only if it contains a spanning tree. So, yeah, if you're confused about how these things are related, try to make a little mind map like this. We've basically created this little world of concepts, which, where the theorems are relating them in not obvious ways. Anyway, that's it for the lecture.